On July 25, 2020, a 984-foot steel structure, empty of cargo, crossed dangerously close to the southeast coast of Mauritius. The motor vessel Wakashio was not driven ashore by a storm. It was brought there by a fatal navigational decision. A deep ocean bulk carrier had been taken far inside the safe offshore margin, towards shallow water where there was no room left for error. The massive bulk carrier was dead in the water, trapped on a shallow reef near internationally important wetlands and protected marine areas off the coast of Mauritius. The casualty carried zero commercial payload, but its internal tanks held about 4,000 tons of fuel and oils, including very low sulfur fuel oil, diesel, and lubricants. A catastrophic pollution hazard was now rigidly locked onto a fragile marine ecosystem. The Wakashio's dimensions defined the scale of the physical problem. At 984 feet long and designed for 203,000 deadweight tons, it was built to move vast bulk cargoes across deep oceans. On this transit, however, it was sailing in ballast. Ballast defined the hull's profile, not the cause of the grounding. Riding high, the Wakashio exposed more steel once it was in trouble, but the decisive failure had already occurred in the passage plan. The vessel had been brought closer to Mauritius, and on the bridge, attention was drawn toward the search for a smartphone signal. By the time the danger became undeniable, the giant ship was already committed to shallow water. The casualty plowed headlong onto the jagged coral reef at Point Desny. The vast forward momentum, combined with the continuous lateral push of the trade winds, drove the empty hull brutally hard aground. The keel of the enormous unladen giant wedged solid onto the unyielding rocky shelf. The forward motion stopped instantly, but the wind continued to pin the massive steel structure directly against the reef face. The ship was immobilized. The enormous hull was now completely stranded at a highly exposed angle on the shallow shelf. The immediate operational danger was not a rapid sinking. The solid underlying reef shelf physically prevented the massive vessel from sliding down into the deep offshore abyss. The ship was stuck fast, high up on the coral. Instead, the predicament was a profound geometry trap. A colossal, empty steel container was pinned tightly against an immovable barrier. With the bunker tank still inside the stranded hull, the vessel could not move, but the surrounding ocean would not stop. The grounded ship remained on the reef for nearly 12 days before the major fuel spill began, and for about 3 weeks before the hull finally separated. As sea conditions worsened, the shallow coral shelf turned the casualty into an unevenly supported structure. Buoyancy no longer acted evenly along the hull, and the reef loaded the steel locally and destructively. Vast sections of the immense hull hung completely suspended in open water off the edge of the submerged rocky ridges. The Indian Ocean did not stop moving. Heavy, towering ocean swells continually rolled in from the deep and slammed violently into the exposed stern. This relentless wave action initiated a devastating cycle of hydrodynamic hull flex. As a massive swell passed beneath the overhanging sections of the ship, the sheer volume of moving water exerted a powerful upward buoyant force. The heavy stern was forcefully driven upward by the rising sea. As the wave crest passed and the trough arrived, the buoyant support instantly dropped away. The unsupported stern section plunged violently downward under its own tremendous dead weight. The midsection of the hull remained firmly pinned against the hard coral fulcrum. This continuous, alternating cycle of extreme lifting and dropping created immense bending moments across the primary structural spine of the casualty. The destructive physics of longitudinal torsion took hold of the enormous vessel. The long steel hull was subjected to severe bending, twisting, and heavy flexing forces with every single passing wave. A steel bulk carrier has substantial structural rigidity, but it is not designed for days of impact and uneven reef support. As sea conditions worsened, the hull pitched, rolled, and struck the seabed until buckling appeared, shell plating cracked, and by August 6th, the damage reached the area near a starboard fuel oil tank. When the tank boundary failed, about 1,000 tons of thick, toxic fuel oil poured into the delicate coastal lagoon, and each movement of the fractured hull risked forcing more pollution through the tear. The structural failure was now cascading uncontrollably. The longitudinal torsion was actively ripping the remainder of the hull apart. The continuous wave action exponentially amplified the severe stress on the newly weakened steel sections. The initial fracture rapidly expanded into a massive structural tear extending entirely across the main deck. The constant heavy flexing of the massive forward and aft sections directly threatened to shatter the remaining intact bunker tanks. The physical disintegration of the giant vessel was rapidly accelerating with every passing hour. Thousands of tons of bunker fuel still remained inside the weakening wreck. The immediate question became unavoidable. How could emergency teams remove it before the ship broke apart? Salvage engineers faced a severe operational trade-off. To reduce the worst spill scenario, emergency teams had to board a rapidly weakening steel platform and extract highly viscous fuel oil from damaged tanks before the hull failed further. The task was not simply pumping liquid from one container to another. Crews had to establish high-capacity hose connections, work through narrow weather and access windows, and transfer the oil onto tankers and support craft while the structure continued to deteriorate beneath them. The emergency transfer continued through a dangerous race against the ship's worsening condition. By August 12th, approximately 3,193 tons of fuel oil had been pumped out. Most of the remaining oil had been removed from the casualty, greatly reducing the worst-case spill scenario. But the operation had not erased the disaster. About 1,000 tons had already escaped into the sea, cleanup was still underway, and the hull was nearing its final break. On August 15th, the casualty changed from one salvage problem into two. The hull tore completely in half, destroying the continuous structure that had once shared weight and buoyancy along a single keel. From that moment, each fragment had to be judged by its own mass, flooding, and trapped air. The primary fracture cut through the empty cargo holds just forward of the main superstructure, detaching the cavernous forward section from the heavy aft machinery spaces. The newly liberated section was a colossal fragment, roughly 740 feet long, with enough trapped air inside its divided cargo spaces to preserve major reserve buoyancy. Freed from the dead weight of the engine room, it rode higher like a giant steel pontoon, still snagged near the outer coral ridges but vulnerable to every swell and wind shift. Conversely, the trailing structural fragment presented a very different physical dynamic. This violently detached aft section housed the main propulsion engine, auxiliary machinery, shafting, and the multi-deck accommodations block. Compared with the cavernous forward holds, the stern was far heavier, more compact, and less buoyant. Once separated from the forward hull, it remained hard aground on the reef, pinned by its machinery weight and by the broken geometry of the wreck. It was not a free, floating hazard like the section. It was an embedded, surf-beaten wreck that would have to be removed in place. The salvage plan therefore split immediately. The buoyant forward section demanded towing, control, and offshore disposal. The embedded stern demanded localized cutting, lifting, and extraction from the reef. The first priority was the forward section. Once released from the reef, it had to be controlled before wind and swell carried it back toward protected water. The engineering teams faced a severe decision flip. Rather than save the largest intact piece, Mauritian authorities chose to tow it offshore and scuttle it in deep water. Its torn aft end made any long-distance tow a risk of flooding, loss of control, renewed pollution, or a new navigation hazard. Executing this operation required immediate towing intervention. Ocean-going tugs entered the hazard zone while salvors boarded the pitching section and secured towing hawsers to the deck bits near the forward peak. Once the gear was locked, the tugs applied steady strain until the section slid backward, dragged its torn aft edges clear of the reef, and floated free. The tug slowly towed the steel fragment away from the coastal sanctuary. Its sheared hull generated immense drag in the swells, forcing the convoy to proceed carefully toward a designated offshore drop zone deep enough to keep the wreck clear of future navigation and fishing risks. Once the flotilla reached the selected offshore position, the deliberate sinking sequence commenced. The forward section had to lose reserve buoyancy in a controlled way. Harmful substances had been removed as far as practicable, and salvors accelerated flooding by opening the structure to the sea, including cuts through bulkhead areas associated with cargo spaces. As seawater entered the holds, trapped air vented through the open deck hatches and the steel section began to settle lower in the water. The open aft section finally dipped permanently beneath the ocean surface. This allowed thousands of tons of dense seawater to cascade entirely uncontrollably into the cavernous interior. The structural balance of the hull completely collapsed. The towering forward suddenly pitched violently upward into the sky as the heavily flooded aft sections aggressively dragged it down. The massive steel fragment instantly initiated its final vertical plunge. The immense structure rapidly accelerated downward, slipping entirely beneath the turbulent ocean surface. The forward section disappeared into the Indian Ocean at a reported depth of about 10,400 feet. Removing it from the reef area, the operation then turned back to the massive steel island still embedded on the protected coral shelf. To clear the final wreckage from the delicate marine sanctuary, engineers needed a mechanical solution, a grab capable of exerting exactly 5,000 tons of crushing force. The aft machinery and accommodation section remained pinned on the shallow coral shelf by its weight and broken geometry, making towing or refloating impracticable. The remaining wreck could not be treated like a simple towage problem. Dragging the embedded stern across the reef would risk further physical damage to the already injured marine environment. The salvage response therefore had to be localized, mechanical, and piece by piece, removing the wreck from the top down, rather than pulling the whole structure away in one destructive movement. The engineering teams brought in the specialized crane barge Hongbang 6. This massive maritime platform was heavily equipped with specialized heavy-lift cranes designed specifically for extreme mechanical dismantling. Instead of rigging cables to lift entire massive structural blocks, the crane utilized an immense mechanical grab. The massive jaws of the heavy steel grab were carefully lowered directly down over the shredded aft sections of the stranded casualty. Operating in highly constrained weather windows between the intense Indian Ocean swells, the specialized crane systematically engaged the mangled steel structure. The heavy mechanical jaws closed aggressively around the thick outer shell plating and internal steel framing. The massive hydraulic systems drove the immense mechanical grab shut, physically biting directly into the heavy steel superstructure. The immense 5,000-ton closing force effortlessly crushed the thick steel plating. It physically sheared through dense bulkheads, heavy deck beams, and thick steel ladders. The heavy crane steadily tore the rigid aft section apart, violently ripping away massive, jagged chunks of raw steel directly off the exposed upper decks. The methodical extraction process was agonizingly slow and incredibly precise. The heavy mechanical grab repeatedly descended, clamped tight, tore away damaged steel sections, and lifted them clear of the remaining structure. The torn fragments were swung over and lowered onto receiving barges positioned alongside. Larger components demanded separate handling. One of the greatest challenges was the main engine, a massive unit that had to be exposed and lifted after the surrounding structure had been broken down. Piece by piece, the crane barge reduced the embedded stern from the upper works down toward the keel structure resting on the reef. The constant heavy surf relentlessly pounded the specialized crane barge, forcing the salvors to frequently suspend operations and physically retreat when the massive swells grew too dangerous. The harsh winter storms severely compressed the available operational windows. But the engineering team systematically returned to the reef after every violent weather cycle, rigorously continuing the mechanical extraction. They methodically stripped away every remaining section of the embedded stern, right down to the final heavy keel plates resting on the coral rock. The heavily loaded transport barges continuously shuttled the massive torn steel chunks securely back into Port Louis. Once in the port, the heavy steel fragments underwent localized depollution and cleaning before being processed and shipped out for recycling. By early 2022, the heavy lift engineers executed their final mechanical removals. The massive structural hazard that had once threatened the shallow coastal shelf was gone. But the removal of the wreck was not the same as full ecological recovery. Oil had already contaminated the southeastern coast, and the long-term condition of nearby mangroves, sediments, coral, and lagoon habitats remained a separate environmental question requiring continued monitoring.